Baltimore, Maryland. The Space Telescope Science Institute. 2:43 in the morning. A planetary scientist is alone at her workstation. The building is quiet. The rest of her team went home hours ago. She stayed because the data pipeline from the James Webb Space Telescope finished processing 40 minutes ahead of schedule. And what loaded onto her screen is something she has never seen before in 22 years of studying planetary atmospheres. She leans forward. On her screen is not a photograph. It is a three-dimensional map. Over 1,000 individual slices of spectral data assembled into a vertical portrait of a planetary atmosphere stretching 5,000 kilometers above the cloud tops. A world rendered in depth for the first time in history. She runs the temperature profile. She stops. She runs it again. The heating peak and the ion density peak are at completely different altitudes, separated by thousands of kilometers of planetary atmosphere. Two independent processes operating in two different regions simultaneously, in ways that every existing atmospheric model says should not be possible on this planet. She pulls up the 30-year cooling record. The trend is still there, still ongoing, still unresolved. She sits back in her chair, not with confusion, with the specific, unsettling recognition of a scientist who has just watched a model she trusted for 3 decades quietly collapse under the weight of real data. She types 4 words into the team message thread. We need to talk tomorrow. Because what the James Webb Space Telescope has just revealed about Uranus, the planet that every textbook described as cold, featureless, and scientifically unremarkable, is not a confirmation of what we thought we knew. It is the systematic dismantling of it. And through the lens of theoretical physics, through the framework that governs how energy behaves inside ice-giant atmospheres, and how magnetic fields at cosmic scales shape the architecture of worlds, what this data describes is not just a mystery about one distant planet. It is a fundamental challenge to the physics models we have been using to characterize the most common type of planet in the entire Milky Way galaxy. To understand the full weight of what the James Webb Space Telescope has now delivered, we need to go back to the last time humanity got a close look at Uranus. Because that encounter, brief, historic, and fundamentally incomplete, is where this mystery began. January 24th, 1986. NASA's Voyager 2 spacecraft completed the only close approach flyby of Uranus in the history of human spaceflight. Launched in 1977 on a trajectory calculated to exploit a rare planetary alignment that occurs only once every 176 years, Voyager 2 had already completed historic flybys of Jupiter and Saturn before arriving at the 7th planet. Its encounter with Uranus lasted days, a fleeting window of proximity compared to the decades of distance on either side. But its instruments measured the planet's basic physical parameters with a precision no Earth-based telescope could approach. What Voyager 2 found seemed, at first, to confirm the prevailing model of Uranus as a quiet, static world. The upper atmosphere registered temperatures of negative 224 degrees Celsius, making Uranus the coldest planetary atmosphere in the entire solar system. Colder than Neptune, despite Neptune being farther from the sun. That anomaly alone deserved more attention than it received at the time. But the broader picture Voyager painted was of a world in thermal equilibrium, slowly radiating the small amount of energy it received from the distant sun. Stable and unremarkable. That picture began to fall apart in the early 1990s. Starting approximately 5 years after Voyager's flyby, ground-based observatories monitoring Uranus's upper atmospheric emissions began detecting a trend that the standard models could not account for. The upper atmosphere was cooling, not fluctuating around in equilibrium, not oscillating seasonally, cooling continuously, systematically, year after year, across a time baseline that now extends more than 3 decades. To understand why this is physically extraordinary, we need to establish what thermal equilibrium means for a planetary atmosphere. Every planet in the solar system receives electromagnetic radiation from the sun and re-radiates that energy back into space as infrared emission. For a planet in thermal equilibrium, energy input equals energy output. The net thermal state remains stable over time. A planet as distant as Uranus, receiving solar flux approximately 370 times weaker than Earth, should reach equilibrium relatively quickly on geological timescales and then remain there. Its atmospheric temperature should be stable at the equilibrium value dictated by its distance, albedo, and greenhouse characteristics. A continuous, multi-decade cooling trend violates this expectation fundamentally. For the upper atmosphere to lose heat continuously, something must be actively removing thermal energy from the system at a rate that exceeds the incoming solar energy budget. The physics demands a mechanism, an active process, an energy transport pathway, a structural feature that is continuously draining heat from the upper atmospheric layers. For 30 years, that mechanism remained unidentified. Not because scientists were not looking, but because Uranus was too distant, its atmospheric emissions too faint, its upper layers too difficult to resolve with any existing instrument. The cooling anomaly sat in the scientific literature like an open wound, documented, confirmed through multiple independent observational campaigns, but unexplained. A cold case in the most literal astronomical sense. And it would remain a cold case until an observatory came online with the sensitivity to see not just the surface of that atmosphere, but through it, to map its vertical structure layer by layer, altitude by altitude, from the cloud tops all the way up into the ionosphere thousands of kilometers above. The James Webb Space Telescope was that observatory, and what it found when it finally stared at Uranus for 15 uninterrupted hours was not the answer to one mystery. It was the revelation of a far deeper one. The James Webb Space Telescope is, by any engineering metric, the most sophisticated scientific instrument in human history. To understand what it accomplished when turned toward Uranus, you first need to appreciate the technical leap it represents over every predecessor. JWST's primary mirror spans 6.5 meters in diameter, nearly 3 times the aperture of the Hubble Space Telescope, and is composed of 18 hexagonal gold-coated beryllium segments deployed in deep space at the second Lagrange point, approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the gravitational influences of Earth and Sun balance in a way that allows a telescope to maintain a stable orbital position, while its 5-layer sunshield, each layer thinner than a human hair, collectively the size of a tennis court, keeps the observatory cooled to below negative 233 degrees Celsius. This thermal stability is not aesthetic. It is functional. At those temperatures, JWST's infrared detectors can resolve thermal emissions so faint they would be completely invisible to any warmer instrument. The key instrument deployed for the Uranus observation was NIRSPEC, the near-infrared spectrograph. NIRSPEC does not simply capture images, It performs what spectroscopists call integral field spectroscopy, simultaneously collecting spectral data across a two-dimensional field of view, producing a data cube in which every spatial position contains a full spectrum. This allows researchers to extract not just brightness information, but chemical composition, temperature, velocity, and particle density at every point across the observed region simultaneously. An international research team trained this instrument on Uranus and held it there for nearly 15 continuous hours, almost exactly one full rotation of the planet. During that observation window, the team collected more than 1,000 individual spectral data slices, capturing the faint infrared glow of ionized hydrogen molecules, specifically the H3 Weiss ion, a triatomic hydrogen molecule that forms when cosmic rays or energetic particles ionize molecular hydrogen in the upper atmosphere. H3 Weiss is one of the most important diagnostic molecules in planetary science, precisely because it is extremely sensitive to temperature and density conditions. Its emission intensity and spectral line shapes encode information about the physical state of the atmosphere at the altitude where it forms. By mapping H3 Weiss emissions across the entire visible disk of Uranus and at multiple altitude levels, the team assembled something that had never existed before in the 40-year history of planetary science following Voyager 2's flyby. A true three-dimensional structural map of Uranus's upper atmosphere, extending from just above the visible cloud deck all the way up to approximately 5,000 kilometers altitude, reaching into the ionosphere, the charged upper atmospheric layer where the planet's magnetic field and the solar wind interact most directly. The Kaku lens frames this achievement in its proper conceptual scale. String theory's approach to dimensional analysis, the idea that the observable universe contains layers of structure accessible only to instruments of sufficient resolution, applies directly here. For 30 years, Uranus presented a two-dimensional facade to human observation, a disk, a spectrum, a temperature reading. Webb converted that facade into a volumetric data set. It added the third dimension that the physics had always demanded. And in that third dimension, the anomalies became not more confused, but, for the first time, coherent. When the three-dimensional atmospheric map of Uranus was finally assembled, and the scientific team examined its temperature profile, the first result was both clarifying and deeply unsettling. For decades, based primarily on Voyager 2's 1986 measurements, the scientific consensus described Uranus's upper atmosphere as uniformly frigid, a frozen shell hovering near negative 224 degrees Celsius, consistent with the planet's extreme distance from the sun and its apparent lack of significant internal heat production. The assumption of uniformity was not arbitrary. Without the ability to resolve vertical structure, a single temperature measurement from a flyby instrument represents a spatial average, a blend of contributions from multiple atmospheric layers. Uniformity was the simplest assumption in the absence of contradicting data. Webb's three-dimensional data contradicted it completely. The new observations revealed that Uranus's upper atmosphere is dramatically non-uniform in its thermal structure. At altitudes between approximately 3,000 and 4,000 kilometers above the cloud tops, deep in the ionosphere, temperatures rise to approximately positive 150 degrees Celsius. This is not a warm region by Earth standards, but relative to the negative 224 Celsius measured at lower altitudes, it represents a temperature gradient of nearly 400 degrees across a vertical distance of a few thousand kilometers of planetary atmosphere. Now let's apply the physics of atmospheric heating to understand why this gradient is so anomalous. Temperature increases with altitude in a planetary upper atmosphere are not unprecedented. They occur on Earth in the thermosphere, where solar ultraviolet radiation directly heats the uppermost atmospheric layers. This process is called solar UV heating. On Earth, it produces thermospheric temperatures of approximately 1,500 degrees Celsius at peak solar activity. The mechanism is well understood. High-energy UV photons dissociate and ionize molecules at high altitude, depositing their energy as heat in the process. But Uranus receives solar flux approximately 370 times weaker than Earth. The UV heating budget available to Uranus is a tiny fraction of what drives Earth's thermospheric temperature profile. Theoretical models of Uranus's upper atmosphere, calibrated against this solar flux budget, predict thermospheric temperatures significantly lower than what Webb measured. The positive 150 Celsius reading at 3,000 to 4,000 kilometers altitude is warmer than the solar flux alone can explain. Something is supplying additional energy to those upper layers, an energy source beyond what the distant sun can provide. This is called the energy crisis of ice giant atmospheres, a well-recognized but unresolved problem in planetary science that applies not just to Uranus, but to Neptune as well. Both ice giants display upper atmospheric temperatures substantially higher than solar heating alone can sustain. The theoretical candidates for this additional energy source include wave heating, the propagation of acoustic and gravity waves upward from the lower atmosphere, dissipating their energy as heat at higher altitudes, Joule heating, driven by electrical currents induced by the planet's magnetic field, and particle precipitation from the magnetosphere, depositing kinetic energy into the upper atmospheric layers. Webb's data added a new and critical dimension to this energy crisis. The temperature profile was not the only structural surprise. When the team examined the distribution of H3 ion density across the three-dimensional atmospheric volume, the result produced what planetary scientists recognized immediately as a diagnostic mismatch of fundamental importance. Ion density peaked at approximately 1,000 kilometers above the cloud tops. Temperature peaked at 3,000 to 4,000 kilometers, 2 to 3,000 kilometers higher. The regions of maximum heating and maximum ion production were not co-located. They were separated by vast vertical distances. In theoretical models of planetary ionospheres, this spatial separation carries specific physical meaning. Ion production in a planetary upper atmosphere is driven primarily by two processes: photoionization, the removal of electrons from molecules by solar UV photons, and particle precipitation, where energetic charged particles from the magnetosphere descend along magnetic field lines and ionize atmospheric molecules upon collision. Both of these processes deposit their ionizing energy at specific altitude ranges determined by the energy spectrum of the ionizing source and the density profile of the neutral atmosphere. Atmospheric heating, on the other hand, can be driven by completely different mechanisms operating at different altitudes: wave propagation, Joule dissipation, or direct magnetic energy input. If the heating mechanism and the ionization mechanism are the same process, temperature and ion density should peak at similar altitudes. If they are different processes, the peaks will be separated. Webb's data shows them separated by thousands of kilometers. This is a direct observational confirmation that two independent physical processes with different energy sources different spatial scales, and different driving mechanisms are simultaneously operating in Uranus's upper atmosphere. The energy budget of this planet is not driven by a single dominant process. It is the output of a complex, layered, multi-mechanism system whose full physics has not yet been characterized. The music of the spheres, as the Kaku lens frames it, is playing in multiple registers simultaneously on Uranus, a symphony of strings resonating at different frequencies in different atmospheric layers. The question that Webb has now placed at the center of planetary science is not simply what is heating Uranus, it is what is orchestrating the interaction between its magnetic architecture, its particle environment, and its thermal structure across 5,000 kilometers of atmospheric depth. That question leads directly to the most bizarre feature of this planet, and the most dramatic visual discovery Webb produced when it turned its gaze toward the ionosphere. The chaotic magnetic engine at the heart of Uranus, and the dark band that engine carved into the sky. The data only gets stranger from here. Uranus breaks every rule a magnetic field is supposed to follow. On Earth, the rotational axis and magnetic axis are nearly aligned, separated by just 11 degrees. That alignment gives us a stable, predictable magnetosphere. Auroras form in neat oval rings around the poles. The physics is orderly. Uranus throws that rulebook into the void. The planet itself is tilted 98 degrees, rolling around the sun on its side like a barrel. But that is only the beginning. Its magnetic axis is tilted an additional 60 degrees relative to its rotational axis. And the field does not even pass through the center of the planet. It is offset, displaced. As Uranus rotates, its magnetic field does not spin cleanly. It tumbles. It wobbles. It twists through space in a chaotic, asymmetric cycle that makes every other planetary magnetosphere in the solar system look simple by comparison. Through the Kaku lens, through the theoretical framework of how magnetic topology governs energy transport in 11-dimensional hyperspace models, Uranus represents a natural laboratory for physics that most planets never demonstrate. Its geometry is so extreme, it forces every theoretical assumption about magnetosphere-atmosphere coupling into direct observational test. And Webb delivered that test with precision. The three-dimensional atmospheric map revealed two distinct bright auroral bands positioned near the predicted magnetic pole regions, exactly where theoretical models said they should appear. That alone was powerful validation. But what Webb detected between those two luminous bands stopped the team cold. A dark region, a visible gap, a band where both the atmospheric glow and the ion density were significantly depleted, a structural void carved directly into the ionosphere by the geometry of Uranus's own magnetic field. This is not an artifact. This is not noise. It is the direct visual signature of magnetic field lines determining where energetic particles can descend into the atmosphere and where they cannot. In the bright bands, field line geometry channels particles downward, creating intense auroral emission. In the dark band between them, the field configuration blocks or diverts those particles entirely. The result is a visible magnetic shadow, a gap in the sky produced not by absence of atmosphere, but by the architecture of an invisible field. Similar features exist on Jupiter, but on Uranus, the effect is dramatically amplified by the field's off-center tumbling orientation, creating asymmetries and structural contrasts that Jupiter's cleaner dipole geometry never produces. This magnetic architecture now explains the temperature mismatch Webb identified. The chaotic field is pumping energy into the atmosphere unevenly, driving intense heating at certain altitudes through joule dissipation and particle precipitation, while ion density concentrates elsewhere. The two-process, two-altitude structure is not a coincidence. It is the direct atmospheric fingerprint of the most geometrically complex magnetosphere in the solar system. Uranus is not cold and dead. It is a dynamic system, magnetically violent, thermally complex, structurally layered, hiding its true nature behind a featureless blue facade. And here is why that matters beyond one planet. Ice giants like Uranus are now believed to be among the most common planetary types in the Milky Way. For years, when astronomers detected distant exoplanets of similar mass and radius, we had no detailed physical template to apply. We were modeling billions of worlds using assumptions built on a single, blurry Voyager snapshot from 1986. Webb just replaced that snapshot with a forensic map. A map of how energy flows through an ice giant atmosphere. A map of how magnetic geometry sculpts ionospheric structure across thousands of kilometers of altitude. A map that will now serve as the physical baseline for characterizing every ice giant world discovered in the galaxy going forward. The 30-year mystery of Uranus's cooling atmosphere is not fully solved. But for the first time, we can see the engine behind it. We can trace its structure. We can watch it operate. The next step requires going back. A dedicated probe. A direct atmospheric entry. A mission to the planet that hid its complexity behind 4 decades of apparent silence. The James Webb Space Telescope did not close the story of Uranus. It proved the story was only just beginning.